Good day to you. This is a Thursday, the 24th day of July 2025 from Chico, California. Over here you will see the Bošković force curve, very well known in Europe, not very well known in the United States yet. One should have to assume it's only a matter of time, but I am an American and I do know about the Bošković force curve, and I've read most of the literature that has surrounded this amazing rediscovery of a force balance system for the atom. This is a rather crowded diagram, I should have to say. Bošković notes that himself. This was published in 1745. There were actually 3 editions of the very famous now Theoria, Philosophiae, Naturalis, which is a somewhat long book that had been written in Latin, but it has been translated into English and quite a few other languages. I own 3 copies of this, and I also have access to the online versions, which you will be able to get for free if you wish, so you can read this as well. Although it would help to have some introductory knowledge that would lead up to a full appreciation of this most amazing discovery by the greatest scientist in history. That's the beauty pageant contest. You don't have to agree with my subjective opinion. Nevertheless, I'm throwing in my vote. Alright, so what is it? It is a series of curves, as you can see. Over to the further left, you'll see what is called the ordinate axis. And that is simply what we today call the y-axis, the second dimension of this planar diagram. So this is a 2D projection of what? What is this? This is a diagram of the Bohr atom over a century before the atom was discovered or any of the components of the atom. Bošković lived right in the shadows, you might say, of Sir Isaac Newton and Herr Leibniz, Gottfried Wilhelm Leibniz. They both died in the first quarter of the 18th century, which we would call the 1700s if we want to name the century after the numbers that are actually in it. You'll see 3 humps, and you'll see an asymptote to the far right, and then you'll see a second asymptote, and then on the other side of the ordinate, that is the y-axis, going through the origin on the horizontal line, on the other side is simply a reflection. A reflection of what? An electron shell. This accurately and intensively defines the proton-electron system of an atom that had not even been discovered. So Bošković got this from first principles, which borders on metaphysics. That's why the term natural philosophy for science at this level of interpretation is called both natural and philosophy. Natural means it applies to the universe, which is sometimes called nature, but philosophy is not science. But humans need philosophy to interpret science. That is the meaning, a very specific meaning of philosophy. It's not philosophizing in the general rhetorical sense. This is not part of the quadrivium or trivium, if I'm even pronouncing those words right, the standard. It's like what we would call reading, writing, and arithmetic. Why are there 3 humps? That's arbitrary, and Bošković points out that it is arbitrary. If this were not arbitrary, it would deal with the section of the periodic table where the shells are counted from 1 to 7 is the current limit, but there is no known limit. So the upper bound of what can be measured would be 7 electron shells. You can say electronic, but you have to be cautious because that has two meanings. This would be an atom with 3 shells. Why? This would be counting the number of curves measuring above the line. If you were measuring below the line, you can see there are 4. And that will be always the case, that one side or the other of this relationship will be off by 1, but not really, because if you look over here, there is the 4th curve that corresponds to this curve, which is only a half curve. And this curve over here is only a half curve. Those are orthogonal. They're at a right angle. But it's not a linear right angle for the reason that that line that's going up and down is nonlinear in all parts. There's no linearity in the curve. It never straightens out. And what that means is that at its two ends, this end goes up asymptotically to the ordinate. We need to know what that ordinate represents. You also need to know what the abscissa represents, which is the horizontal line. That is space. And it's the only space in this projection. It's only on the line. Anything that is off the line is non-spatial. So what is that curve representing? The abscissa, which we call the x-axis, is strictly what you and I were taught in school, exactly space. It's strictly speaking to be termed, and learn this term, please, linear, spatial, separation. All three of those words are critical to the term. It's linear. It's not nonlinear. The horizontal line is linear indeed, and it represents distance, which is spatial separation on a straight line according to Euclid. So that is the horizontal aspect of this 2D diagram. What is the ordinate? That is force. Force. Force is incompletely understood to the point of an enormous and violent dissension among physicists, which you're not ordinarily exposed to, but if you would like to be exposed to the absolutely split decision on what is a force in modern cutting-edge physics, if you have 3 scientists in a room, the probability of them agreeing on the definition of a force is less than 50%. 2 of them are most likely to say that, for instance, gravity is a force, and the other one will say no, gravity is not a force. And if you would like a very good introduction from one side of that argument, Dr. Sabine Hassenfelder of Deutschland has produced, I believe, a 20-minute video where she says way too many times, as if she were propagandizing the public, which she has no real reason to do that I can guess at. She says that gravity is not a force. And she stares at you and she opens her eyes and she gets rather emotional about it. So that you know that gravity is not a force. Why does she feel justified in saying that? It's because it does not involve motion. In other words, it's a force without known energy. It's a static force. And that is what this diagram depicts. So now we're going to get into it so you will see what Bošković discovered. So that curve is going through force space, which is an abstraction. It doesn't mean that it actually exists. but it is what is called a measurable. So it exists in some sense, in the same sense really that space exists. Space has no characteristics. That was the opinion in Bošković's day. These days, all scientists agree. When I say scientists, I mean physicists. Physicists who base all of their knowledge purely on mathematics. Always a mistake. That's the name of the game for the past century. Everything is mathematical, and that's why there is a paradoxical system for the quantum mechanical system, and indeed for general relativity, neither of which quite works. It was Einstein who broke the mold on the perception of space that it may have a characteristic. All physicists of the mathematical stripe agree that space now is known to have a characteristic. Do you know what it is? It curves. So does that line. But is it space that's curving? We can say so from a certain perspective, but there is a much better perspective having to do with the concept of a field, F-I-E-L-D. Pardon me for those of you who are well versed in the concept of a field, but it's one of the major discoveries in the history of physics, the concept of a field. It was James Clerk Maxwell who showed that electromagnetism is two perpendicular fields. Isn't that curious? They're orthogonal fields? Yes, they are. Although you don't hear it said very much, opening up any electrodynamics textbook, within the first 3 to 4 pages, it will tell you. The B field, which is representative of magnetism, is orthogonal to the electrofield, and they never occur alone. That is why magnetism is dipolar rather than monopolar, whereas the proton, as it exerts centripetal force, pulling space in, that's where we get gravity from, is from the integral of the protons in a body such as the Earth or the Sun. And we used to think galaxy, but that has been disproved in my research. So when we get to the astronomic scale, we will discover that gravity no longer applies. That is not known yet. All of the confusion in cosmology in trying to interpret the morphology of galaxies and higher scale objects, such as the black hole, all of that is assumed to be based on gravity. That is not the case at large scale. At solar system scale, we know all about gravity. Newtonian physics applies perfectly. If you need to account for time lag in the solar systemic system, then you use Einstein's pseudo-hyperbolic geometry, which uses hypercalculus that a human being cannot do, but a supercomputer can. Also, certain superhumans can do it, for instance, Minkowski and Einstein. But Einstein added to Minkowski's discovery of spacetime. It was Minkowski who discovered it. What Minkowski formulated to formulate spacetime was a 4-vector system that is a 4-component number, where 3 of the components are space and the 4th one is time. Because they're all orthogonal, time has to be signed negatively, and so time becomes imaginary in the system. So what's the difference between Minkowskian spacetime and Einsteinian spacetime? We discovered that in one of the previous 4 videos, but I will summarize it here, of course. Minkowskian spacetime is flat. And what does that mean? It means that space does not curve. There's a footnote to that. Something curves, and you can model it in your mind at least as space being curved. What Einstein did was, he actually, you could say, borrowed, and Minkowski never complained. They were contemporaries, and in fact, I believe Einstein studied with or under Minkowski for a while, so Minkowski picked up on space-time. What Einstein did that changed the whole game, and Minkowski was very generous in my opinion, he said, oh yeah, this is... He took it and ran with it and made something new. What did Einstein do? He took the flat geometry and he mathematically curved it with calculus. That's exactly correctly stated. So Einstein took flat space with a time component, which is imaginary. That's all in Minkowski space, but Minkowski space is not curved, although it is hyperbolic. So you could say that it's curved, but actually the curvature that's desired is not hyperbolic curvature, it's spherical curvature, because gravity exists as a spherical force field. Now, getting back to the concept of force, which is absolutely required understanding to some threshold to understand what Bošković meant by force. What Bošković meant by force is the characteristic of a force field. He did not use the term field, although he defined it exactly the way a field is defined today, at least to a threshold, because in modern physics everything has gone haywire. And the concept of a field, such as quantum field theory, is inaccurate. It proceeds from the wrong axiomatic basis. This solves that problem in physics, which I will now show you. And you do have to concentrate a bit, because there will be at least two places where your mind is going to be exercised in a direction where it's not used to trying to visualize things. Because this graph brings out the hidden dimension of space. And that's profound, because nobody's ever surmised this. So we've been talking about force, we've been talking about the field, and now we're talking about domains. What science works in, and this is a generalization, but it's accurate enough. There's a footnote to everything these days. But science works in the space domain. We now must consider that space is correlated with time in a known way. Do you know what the correlation is? It's called a relationship, which is a geometric term. What is the geometric relationship between time and space in Einsteinian spacetime? Do you know? It's orthogonality. Time is perpendicular to space. You're going to see that that's actually a calculus derivative apperception. What I discovered is the integral solution, which is reality. It's the physical geometry of space-time. So we're now going to understand space-time in a way that none of your physicists and mathematicians understand it. There are reasons for their preferences, but that goes to somewhat psychosociological or socio-psychological issues having to do with cartels, group mind, and financing by governments, and pride. Now, Bošković, having lived and grown up right after Newton and Leibniz died, mastered their calculus. And you do need both forms of calculus. Leibniz had a pronouncedly different angle on the calculus, whereas Newton had a different angle, and when you put them together, you get a synthetic view of calculus, which alone is correct in context. So calculus is involved at the Einsteinian level, but Bošković uses no mathematics to discuss in Theoria, Philosophiae, Naturalis, the Venetian edition of which was produced in 1763, later than 1745. Bošković worked on this natural philosophy problem of particle interaction for most of his life. Definitely the second half of his life, that's really all he worked on, although he was a typical overworked man of those days. These curves that you see are obviously multiple curves. This shows 3, or you could say 4 if you include the 2 ends. But that's already profound, isn't it? Let's make sure that we understand exactly what this graph says. Whenever you see a graph, I'll just say of this type, a 2D projection is the most common diagram or graph. You need to understand the 2 aspects, which are the vertical and the horizontal. Only the horizontal aspect, called the abscissa, we call it the x-axis, sometimes called cosine, if you're computing curvature from the Cartesian plane, which by the way is inaccurately parameterized on x and y. You have to then decide, and hopefully the information is given. It's not given here, but Bošković describes what is the ordinate. What does that represent? It's the metric of that aspect. This metric is spatial separation, linear spatial separation only on the horizontal line. Anything off the line in either direction is not in space. Which might make you wonder, how do we know that this curve is curving the way it does if it's non-spatial? It's because above the line is one force in action, and below the line is another force in action. And now we're going to switch to a more explanatory diagram, which I think you'll find most fascinating. This, once I extend this, excuse me here, while I extend this so you can see the whole graph. There we go. So range in femtometers is the smallest measurable scale, broadly speaking, or not broadly speaking, but minutely speaking. Femtometers are the, you could say, natural unit at atomic scale. So this is atomic scale that we're looking at. So is the previous diagram. But here you will see that there's only one curve. And it's really the 2 ends of the prior curve, you could say, abstractly, I suppose might be the right word there. Let's make sure we understand that. So there is the Bošković curve, and you will see that at, I believe you can see that pointer. I hope you can. That is an asymptotic curve. These curves are not asymptotic, they're algebraic. And this is part of the algebraic curve where it tapers off to infinity. As you probably know, an asymptotic curve is describing a relationship, I'll say in this case, between a straight line and a curved line, where they approach each other, in this case through space, going this way. They continue to approach each other, but they never meet. And that, of course, is the violation of the 5th postulate of Euclid, where that's not really fair, because Euclid only dealt with straight lines. But when you're dealing with one line that's straight and one line that's curved, you see this in the hyperbolic curve, that there are 2 asymptotes that the curve never touches, but it traces both straight lines to infinity, which is a paradox. So we have one asymptote at this end. Over here, you'll see the final curve dips and then comes up, preparing to make another curve, as happened 3 times before. 1, 2, 3. This would be the 4th, but no. You could say it goes in the opposite direction, but it's not opposite, is it? It could have ended with this curve going asymptotically down. Why does it end going asymptotically up? Without answering that question, I want you to notice the relationship between the two asymptotes, which really refers to the curve. When you say the asymptote, you can either be referring to the straight line, that's the usual definition, but here we're not going to say asymptote, we're going to say asymptotic curve, because we're referring not to the straight line with which the curve is asymptotic, but to the asymptotic curve itself, which is an expression of Zeno's paradox. I will say no more. You can look that up if you don't know anything about Zeno's paradox, but it has never been solved, and it's been around for 2.5 millennia. I should probably say something, but I'll bet you could figure it out what Zeno's paradox is. It's when you go halfway to your target, then you go halfway again, then halfway again, you never reach the target. That is true in spheric space, as I'll show you. This is actually the projection of spherical space. Because the two particles are spheres, we know that. That's actually been discovered. Bošković knew that that had to be the case, but the actual proof that an electron or a proton is spheric was not discovered until those particles were discovered. So Bošković was quite far ahead of his time. Just so you have some idea of the impact that Bošković had, he had almost no impact in his lifetime. Very few, if any, books were written, actually none, were written about Bošković's work. It was not understood, but also it was never challenged. It certainly was never refuted. It simply had to wait until the particles that he was talking about were discovered. What did he think that they were? He thought that they were particles, but not the electron and proton. What he figured out is there's a relationship between the electron and proton, which is what this is, or the proton and proton, or the electron and electron. Those are implied. But he didn't know about force, charge. He didn't know about the Coulomb force. And this is not, strictly speaking, the Coulomb force. It's not polaric. Because it's not polaric means like this, where this way is plus and this way is minus. That's how we were all taught in school. And yet that defies what Maxwell actually discovered, which is there are two force fields that are perpendicular. You can look that up if you want. All the textbooks will say it somewhere, because you can't avoid saying it, but it's remarkable that nobody has ever realized that that corresponds to linear orthogonality, but in field space, or here force space. It's not linear space, it's non-Euclidean. A curve is non-Euclidean. That's really all that non-Euclidean means, although it does have meanings we went into in the past 3 presentations. So what does this show? What it shows is that there is a particle at the origin, which is A right here, I'm just circling it. A typical frame of reference is what it is. It's a reference frame, and in science that's always 0. Always 0. Because our number system has a reference frame of 0. If you have a line, it can be proved that the center of that line, based on the balancing of two polaric infinities called antipodes, even at infinity, those have to be points. So it's the balancing of all the points on the center, called the Archimedean of the object, in this case the line, that is null. That is, it doesn't exist. What that means is that you can interpret what the null point is according to the embedding space, which in Euclidean geometry means that it's the origin of distance, which is only positive. So on a ray, you have to start at 0 in order to cut off the line. In order to have a metric, in order to have a metric for distance, you have to start at 0, otherwise 1 has no meaning, which is the index. And so distance would not have a cutoff. The cutoff is 0. Now here, you could say the same thing. You should. Just assume that that is 0. But it's a two-dimensional 0. Because in systematic linear space, you start with a line, which is 1D, and it has a 0. A single component 0. On the Cartesian plane, the 0 is the 0 of the y-axis and the x-axis. So it's a two-component 0. It's just one way you can express that difference. There is a difference. And when you extend it to 3D, which we think defines space and actually does not, although it's superpositional, it's a three-component 0. If you have spacetime, Minkowskian or Einsteinian, and what is the difference again? Minkowskian spacetime is flat. It implies no curvature, although very interesting, because there is a hyperbolicity to this system in 4D, which does not exist in 3D. 3D space is cubic. 2D space is squared, sometimes called quadratic, which means squared. They're squares, obviously. But in 3D, they're cubes. In 4D flat space, they're hypercubes. What Einstein did was he took the hypercubic space of Minkowski and he curved it mathematically with hypercalculus. So it is a computed addition to the structure based on how he construed curvature, which was inside out. And it had to be inside out. It's antispherical. And that's called pseudo-hyperbolic space. It's not strictly speaking hyperbolic. But that's a technicality and a nuance that we don't need to go into here because it's not directly related to what we need to see. What we need to see right now, the first thing you look for in a diagram like this is obviously, what does it say? What is the purpose of this? It's to show that two particles, and we won't say which ones. Well, we will, because it's actually a proton and an electron, but for this diagram. But Bošković didn't know that. So he wasn't talking about a proton and an electron because he didn't know what they were. He's just talking about two general particles. So it's remarkable that he got this. This is an exact depiction of the Bohr atom, which is now accepted by science 100% with a footnote. It's always a footnote because everyone's confused. It has to do with the quantum paradox, but we're getting there. So what does this show? It shows that when two particles, we'll just say that for now, get closer and closer together, that the attractive repulsive force relationship changes. So that if two particles are extremely far apart, this graph, because of the asymptote going this way, shows they feel each other. So if there were only two particles in the universe, they would feel each other at any distance, because it never goes to 0, which is profound. There's actually no 0 in mathematics spherical space. I discovered that. So this is consonant with my discovery. And I have become something of an amateur expert on Bošković's force curve. So I do know what I'm talking about, but in order for it to be science, it has to be communicable by the strict rigorous proof system of science called the scientific method, although that's just the tip of a system of propositional proof. So what does this show? It shows on the curve how with changing proximity, changing spatial separation, the force alternates between attraction and repulsion. Pretty simple, yes? Now it gets interesting. Now on the ordinate going up the y-axis, you'll see there's another curve going off in that direction. And it's simply a mirror image of this one on this side. Because this actually shows a particle, which would be a sphere, at the center, at the origin. Does that particle have a radius? That actually was the subject of a lot of discussion back in Newton and Leibniz and Bošković's day. Their lives did overlap, although Bošković basically was coming of age as the two illustrious mathematicians before him passed off the scene. So he knew both of their... He knew Leibniz's work very well and talks about it, and Newton's work and talks about it, and he greatly admired these two men. And he said, the system that I have come up with is very similar to Newton's and Leibniz's, but is distinguished from either one. In other words, what he found went way beyond what Newton or Leibniz were able to discover in their research into physics. As you probably know, Newton thought there was such a thing as a corpuscle for light, which would be a photon, and Leibniz thought that there was a construction of a particle which he called a monad. And it does get into philosophy because they didn't really have any way to test what they thought about particles. But it was part of the atomistic legacy, which goes back over 2,000 years. Democritus, and I believe it was Lucretius, talked about a fundamental building block of matter, essentially. So, I want to give you a secret on how to read this graph, which will be very beneficial in the long run, although it may not make sense at first. So I'd like you to pay attention to the difference between a dynamically interpreted graph and a statically interpreted graph. And the difference is whether something is in motion or not. That is, you're trying to measure a change as something is happening, or you can look at it as simply a map where there is no motion, and the map shows you anywhere on the horizontal axis you can read up or down to find out the force in units, which Bošković didn't know how to compose the units of force, but these days we do. So now we just want to switch back over to this. And here I'd like you to see that the same asymptote over here goes up, just as in the Bošković force curve, and over here you'll see this asymptote goes into spatial infinity. The natural question you might want to ask now is, what is this asymptote to infinity? It's going to infinite force, which is antiphysical, so there's some subtlety in this diagram. Where is this diagram from? What is this a diagram of? This is taken from Wikipedia in the article called The Nuclear Force, which Wikipedia, right away in the first paragraph, correctly, is forced to disambiguate because there are at least two known nuclear forces. So which one is it? This depicts the strong force. What is that? What this diagram shows can be interpreted in exactly the same way as the Bošković force curve. It's actually just a reduced Bošković force curve, where instead of there being humps representing electronic shells, this is the relationship between two protons at binding range. And it shows you exactly where they bind. So if you picture two protons, one of them is at the origin. Does it have a radius? It does, and we'll see that in a moment. But this proton is somewhere way off in the distance, and now we start action to make a dynamic interpretation. This proton is being pulled, so its attractive force which one is it? It is attractive. I'm sorry, it's not. Although Wikipedia says it is. This is really an interesting conundrum. Which is which? One's repulsive, where the two protons would push away. So we're going to say that that's what this is. It actually isn't, though. It's the opposite. I'm not trying to confuse you, but I'm stating the way I've had to go through this so many times. And I won't go into any stories, but I actually got this backwards in a presentation that got the most views of any of my 1,025 videos in 3 years. So that was quite embarrassing, but it did lead to a discovery. And I've made several major discoveries because of this curve. So we're getting into some enchanted territory, but this is actually a known relationship. None of this is theoretic. But what does it mean? We're going to say, for now, that two protons repel because they have the same charge. They repel. So if you're looking at it that way, what this means is, going off to spatial infinity, that those protons will never meet. Now, what's actually happening with this diagram is that has been overcome. In other words, the two protons, due to one having relative velocity, approaches the other proton, which would repel it if it has insufficient velocity to collide. Right? Because they naturally repel, and the repulsive force goes way up as they get close. But if it crosses a boundary, a tipping point it's called, they actually attract, which would mean that they would bind. And this does show the range of binding. That is a fact, but still we have to answer the question, going up, is that repulsive or attractive? And going below, is that attractive or repulsive? It does make quite a bit of difference which is which. It could be either. Now here on this graph, you probably can't read the hatch marks, but this is force in the fourth power of newtons, which is a measure of Newtonian force. Well named. But going up it's positive, which is how we normally do it, and below it's negative. The line itself, the spatial line, is no force. And let me ask you a question, and try to answer it quickly, because this is not meant to be a trick question. Does the force line intersect with the space line anywhere? And if so, in how many points? It intersects in only one point, at the 0.8 femtometer mark, where the blue line begins to skyrocket and it crosses the space line. That's the tipping point, a highly unstable Lagrangian point, and that is proper to say I discovered that, although that's probably stretching the word discover. I stated it in a way nobody's ever stated it. Where the blue line crosses the horizontal line and goes skyrocketing on an asymptote to force infinity, it's either going to repulsive force infinity, infinite repulsive force, or it's going to infinite attractive force. Which is it? Going up is repulsive. Otherwise, wouldn't they crash together? Actually, no. So this is magnificently baffling, but I am here to give you the key. Very hard to see because there is an innate ambiguity between which is which. Because if this were the electron-proton relationship, it wouldn't be the same as the proton-proton relationship. And you might ask, rather naturally, what happens with two electrons? It's a curve that looks like this, and it's repulsive force. Two electrons repel, and they never collide. The only time two electrons can be in their closest proximity is when they're both in the same shell. And then they basically make a different quantum level for that shell based on the addition of a new electron. In the proton-electron relationship for hydrogen, simplex hydrogen, just one proton and one electron, the electron is attracted to the proton. So here's the proton, the electron accelerates, and as soon as it reaches this tipping point over here, it does this. Watch. The electron is accelerating, and when it reaches that tipping point, it goes into orbit. That's an orthogonal change of direction. That's why the electron does not collide with the proton. It's because two forces are at work. Because the proton exhibits two force fields. Two force fields. You could think of it as one force field that inverts. Here's the proton, whose radius is its centrifugal force. It's repulsive. That's why it makes a position. It's making space. So the proton is a space particle. That's why it has an exact position. The proton has an exact position. It's that origin. You would think of it as zero. But it's a spherical zero. I hope that makes sense. This is new, don't forget. Alright, so... Alright, this is to get the force relation right from the horse's mouth. This is after having clicked on the diagram in Wikipedia, where we can read, and you probably can't read that, the attractive force has a maximum distance of about 1 femtometer. That's at the bottom of the curve, is right above the 1 femtometer mark. That is showing the maximum attractive force. So attractive force is negative. Let's read on to be sure of that. The attractive negative force has a maximum at a distance of about 1 femtometer with a force of about 25,000 newtons. Particles closer than a distance of 0.8 femtometers, that's where the blue line crosses the space line. Where the force line crosses the space line, the force inverts. Where they meet at the tipping point, there is no force. So velocity has to be involved here to overcome the attractive force so that they don't crash together. So what's happening is the proton, using the dynamic interpretation, is approaching, and it is being attracted, and that is depicted by the downward slope. This is counterintuitive, which is why I got it wrong more than once. Because this is not the electrostatic force, which is inverted. It's actually inside the electrostatic force inversion. So this is a second inversion that causes protons to bind rather than repel. They normally repel, but if there's enough velocity, it'll attract. And that's what this shows, is when it starts attracting, then it repels again. And that's the asymptotic curve going up, is toward infinite repulsive force. So going up is repulsive force. So dynamically, this proton is approaching the other, and it's already gotten past the electrostatic limit, and now it's accelerating, just as an electron would. And so you might expect that the proton goes into orbit around the other proton. That's exactly right. That's exactly what happens. I discovered that by an accident, a dyslexic accident. It's more than dyslexia. It's actually quite an easy mistake to make until you see the full dynamic. So, what that means is, this proton is accelerating toward the other one. The curve shows a dip showing that acceleration. That is acceleration. Think of it as going downhill and accelerating. So it's accelerating, but when it reaches the 1 femtometer range, and I believe my pointer will work here. Yeah, right there is where it is still attractive force, but now it's decreasing in this short range between 1 femtometer and 0.8 femtometers. It's still being attracted. So there's still forward velocity. There's actually still acceleration, but it's decreasing. And when the proton reaches here, there is no further acceleration. But if there's sufficient relative velocity and it goes past this tipping point, it's repelled. Right? This is such an interesting, I always re-grok on this every time. What does that mean? It means that the proton is accelerating through this range, and now it's accelerating but not with the same rate of acceleration. The rate of acceleration is decreasing, but it's still accelerating. Here, there's no further acceleration, and it has the velocity that it has without any change. So if it still has velocity, it goes further, whereupon there's a repulsive force slowing it down. So if there's, and you can see now it's extremely short range change with respect to this force line, which is going to infinite repulsive force. So what happens if it goes this far? You can read up and find out that it's now being repelled. So it's going to slow down and stop about here, and then it's going to start to go backwards because of the repulsive force. And when it crosses this line again, it will feel attractive force. So it's going to oscillate and stop right where the two lines meet. And that is the exact radial distance, actually linear separation between the two centers of force, which would be the center of the proton, and both of these are protons. So now you see the radius of the proton. How far is it? It's less than 1 femtometer, but what is it exactly? That's very difficult to say, because two spheres, when they're coming toward each other, you see, well, one is going toward the other one relativistically. It could be either one, but we'll say it's this one. But really, they're affecting each other. So they're They're repelling, but there's still, one of them has relative velocity with respect to the other. So they continue to close distance, but they're slowing down. And where they stop, they can't drift apart because they'll be pulled back and then they'll oscillate, possibly, and stop. So this shows the stop range between the two spheres. But what does that mean? Is it two radii or just one? I'll leave that question open now until the future, well, probably the next video. But this shows where two protons bind. If they're you could think of one as a hydrogen ion and the other one as another hydrogen ion, and when they bind, they make a helium ion, which exists at least on the surface of the sun or in the sun. But that is the binding of two protons. You're looking at it where these two lines cross. That distance is the distance, we'll just say for now, between their centers. And that begins a tremendously important story whose conclusion is the quantum of gravity and the solution to the collapse of the wave function, the disambiguation of superposition, the disambiguation of entanglement, and the fullest description of light thus far, both at emission and absorption, and most importantly to me, transmission. How does that photon go from the atom of the star to the atom of your telescope? How does it know to go on that straight line when it's expanding as a sphere? I'll show you. And it's the most remarkable discovery in the history of science. Thank you so much for tuning in. Thank all of you for your patience, those few of you who are attempting to follow these lectures. You're going to be vastly rewarded. I hope you already have been. Keep looking up. We'll be back with another presentation very soon. And thank you. I find it very difficult to turn this off. I want to tell you more, but I'm exhausted. So we'll be right back. Thank you.